it's my pleasure to introduce someone who I've come to admire greatly and begun to work with in just a tiny way. In the Mitchell Center, we tackle a lot of problems that are kind of the intersection between economic development and environmental protection, and one of those is, what's the world's energy future supposed to look like? Are we supposed to burn more fossil fuel? Are we supposed to have all renewables? Are we supposed to have nuclear? A lot of tough questions, no simple answers, but figuring that out requires that we pay a lot more attention to people's perceptions of those alternatives, and it just happens that we got an amazing researcher here who can help us figure this out, and that is Nicholas Giudice. He's an associate professor in the School of Computing and Information Science. He did his PhD out in my part of the world, California, the University of California at Santa Barbara, where he got a degree in cognitive and biological psychology. I think that's what he did, a postdoc in cognitive and biological psychology at the University of Minnesota, and before that his PhD in cognition, perception, and cognitive neuroscience, part of the psychology program at UC Santa Barbara. So what was exciting to me is we had an opportunity to launch some new projects in conjunction with the Mitchell Center, and Nick contacted me and basically said, hey, I think I have an idea to help the people who are working on wind power figure out what it's actually like to be around wind power. And this is where his expertise in virtual reality has proven so important, and I'm going to let him take it from here.
Well, thank you, David. One prefatory note. I like to be connected with my audience, but I'm obviously not going to see you if you look confused, you have questions, you fall asleep, you're prepared to throw a tomato, what have you. So please feel free to make noises of assent, dismay, asking questions, jump up and down, whatever. One other thing, I have my guide dog behind the podium here with me, so if you see me kind of lean over and talk to something, I may be crazy, but that's not one of the reasons. So, next slide. First, I want to thank some of the collaborators here from SSI on this project, Mario, Caroline, and Shannon, and from VEMI Lab, Rick Corey, Tim McGrath, who did a lot of the actual work on coding of these things, and a bunch of other students that were involved. Thanks a lot. Thank you to Nikita here for helping with the slides as well. Next. So I have 3 goals of this talk, but I'll start with the caveat that this is really an overview talk about technology. It's not a data talk. I'm used to giving data talks, so but I want to kind of give this overview because I think it'll be helpful. So my first goal is to introduce you to what virtual reality, or VR, and augmented reality, or AR, is. And I apologize to some of you here, that's going to be old hat, and that part of this may be boring, but a lot of you it's not. And I think it's, I hope to convey how these technologies are really great tools for all types of applications. I'll talk about some of them. But my goal here my hope is to generate ideas from a bunch of the folks that are in this room, forge new collaborations, talk to people about how you can say, hey, I could complement what I'm doing, or I could augment what I'm doing, or you could show off what I'm doing, I'm being you in this case, for your research, and then hopefully tie some of the things that I'm talking about to SSI-related research, or wherever you're coming from. My second goal here is really just to briefly discuss why these technologies are the cutting edge of information visualization, and I really think they are. And my third and final goal gets to the advertised title of this talk initially, and I'll tell you a little bit about what we've been doing in the lab over the last few months on this idea of using these technologies to visualize wind energy installations. And that's one of the SSI Emerging Opportunity projects that David mentioned. So, a little background about me. David kind of covered this. My expertise is in experimental psychology and cognitive neuroscience. And my position here at Maine is in the School of Computing and Information Science. And so the bridge here is essentially that I'm interested in designing and conducting experiments, human experiments. Most of them are behavioral. Some of them deal with neuroimaging. But essentially to understand human information processing in the brain between different senses, vision, touch, hearing, what have you. And I'm particularly interested in spatial information. So if you feel you see the edge of this podium, the brain doesn't give a damn that you're feeling it or seeing it from different senses. It cares that it's doing computation of, in this case, a 90-degree angle, and so it processes that information from different senses. I'm very happy to say that the Nobel Prize just came out for the first time in spatial, a guy that does spatial neurocognition, John O'Keefe. So that's kind of exciting for people in our little niche. Anyway, I use these kind of these basic results, this basic research, to design multimodal interfaces and interactive technologies that are really aimed to tap kind of what's the best way that our nervous system can take information so it's maximally perceptible, so it really is able to be processed in the most efficient way, which makes it more usable, makes it more understandable. And so that's what brings us to to virtual reality and augmented reality. So a good starting question here, I guess we could say, is what are these technologies and why do they work? And my emphasis here is both on the psychological factors and the technological factors. And it turns out at the end of the day, the psychology is actually more important than the technology, as I think I'll demonstrate. So next. So this is a big, sloppy, formal definition of what VR is. Shorter, I think, working definition is simply, any computer-simulated world rendered from a first-person perspective. So essentially rendered as if you're in the environment versus a third-person perspective where you're looking at it from above or outside. These usually include 3D visual information, but what we do, and a big interest of mine, is they also can include lots of other information. So you can have renderings from other senses, auditory, touch, and you could have first-person, completely auditory rendered virtual reality based on what's called spatialized sound. So instead of seeing what's around you, you hear it, and as you turn, you hear things moving around you, and you can develop essentially auditory images, much like you get visual images. There are 4 key elements that I'm going to talk about here, and my point is really that I think these will help kind of explain what the process is and why it works. Okay, next. The starting part for if you're going to make some virtual world, you need to start by creating a 3D computer-based model of some environment. It can be a real environment, you can make this room, it can be a totally made-up environment, doesn't matter. But you need to make a world. Besides the spatial relations of the world, the virtual model includes things like the position and orientation of objects in the environment and the rules that govern the movement, so movement between the objects, movement between people, and what have you. And what's important to remember here is what I call the first law of virtual reality. A bit pompous to define the first law of virtual reality, but people screw this up so much it needed to be done. So the first law of virtual reality is simple. The virtual world is only as good as the underlying data that it's created from, and the rules implementing the simulation. So the data and the rules governing the movement and what have you. So for example, if the university came to me and they said, all right, Nick, and whoever else in the VEMI lab, we want you to make a virtual model of the student union. Great, send us a BIM, a building information model, or some CAD files, we'll make it. But if it doesn't include the information desk in those models, then your virtual model isn't going to include the information desk. Seems obvious, but you'd be amazed how many people say, well, where's the information desk? I don't know, where was it? It wasn't in your model. It's virtual reality, it's not magic reality. So that's my take-home soapbox on that. Another thing that people forget, and they're trying to be fancy, you want to make things that are cool and flashy and what have you, that's great. But to be realistic, the virtual world must follow normal rules. So, example, think of rules of perception. If you're talking about something that's going off in the distance, like a railroad tracks, they should converge. That's what vision does. So if you make your model so they don't converge, looks like crap. People say it's not believable. It's not going to work. Follow physical rules. So if there's something drops in VR, it should follow normal physical, it should fall based on gravity. If you have some other gain or some other thing when something moves, it won't look right. Now, VR physics are based on real physics, so that's good, and you can, a lot of the stuff's already in there, but you can play with collision physics and all different types of things. But you also can make it so they don't follow traditional laws. So for example, it's easy to make people fly, right? A lot of times you have people flying through the world. You can have the shortest distance not be Euclidean. You can go through a wormhole. But generally, the closer the virtual world is to reality, the more believable it is, and that's really what we're aiming for. Next. Another important aspect here is interactivity. So virtual worlds are most effective when the user can directly interact with the system and the system responds to their actions. So the bottom line here is that most interfaces that we use are indirect mappings, especially for movement. So if you have a mouse, you want to move something on the screen, you have to move the mouse around. When you're moving your hand on a mouse, that's not what you really want to move. You want to move something on the screen. Well, that's why I believe in colors. So the real advantage and the key thing that separates immersive virtual technology is that the movement is direct. It's happening. You're freely moving your body. You're freely using gestures. It's natural and intuitive. So if you want to twist around, if you want to go up and down, kick, spin, whatever, assuming we're using appropriate tracking, it allows you to move in three spatial dimensions, what's called 6 degrees of freedom. And you see that 6 degrees of freedom are kind of spelled out, how these pitch, roll, yaw axes. And that's really important for making this seem real. Next. Sensory feedback is another thing that allows virtual reality systems to update the information that the user sees, what they're hearing, what they're feeling. Obviously that depends on what's in the underlying model. But the important thing here is that the user is able to, that this stuff all changes as the person moves in 3D space. So we had people moving in 3D space in the last slide, but if the world doesn't change in correspondence with your movement, then it doesn't seem very real, because that's what happens. When you move in the world, as I walk toward this, it changes its visual angle. As I walk away, it changes. These things should all happen in the virtual reality, and that's what really makes it seem different than other types of technologies. This is done by tracking the body and tracking the head as it moves. There's different technologies to do this, but generally you're wearing what's called a head-mounted display, or HMD, and there's lots of examples of this. This image here is of an Oculus Rift, and a lot of the people here may be familiar with these Rifts. They came out and kind of made people suddenly realize that VR is out there. And what's great about these is that they're cheap. This is a commercial market. They're $300, right? And the VR helmet that we have in my lab is $40,000. You don't put that in your living room, right? So it's great to be able that these are getting into a situation now where we can have real stereo vision. So essentially you're projecting images to both eyes at a little bit different angles, so you can really simulate depth and stereo vision. HMDs include headphones, so we can do that spatialized audio that I talked about. So you can add audio to visual, which is how normally we experience the world, and we can do complete audio, like I mentioned. Some systems now also use what's shown here is a data glove or a force feedback glove. So now, instead of imagining that if you see a glass and you reach and you pick it up and there's no weight to the glass, it doesn't seem real. So you can start adding this type of more technology to add more sensory feedback. Next. Okay, this is the most important. The fourth and final aspect refers to what's called immersion. And immersion is a feeling of being situated, or a feeling of being embodied within the virtual environment. You might also hear this called presence. So essentially this occurs when you are fully engaged with the virtual environment and you lose contact with the external world. So it's when you believe that you are there, essentially. It's a psychological phenomenon, but it's critical for what makes immersion is why VR is compelling. It's why these systems are so different than other systems that you use, because you believe that you're there. So we have the image here is a plank between two platforms, I believe. Is that up here? Yeah. So this is something we show in the lab, and I love it because it really shows immersion. So this is going, I think it's modeled at 16 feet above the water. Okay, we have people come in the lab. We say, they take the HMD off, and we have an actual physical plank that this virtual one corresponds to. Walk across the plank. So they walk across the plank. It's a small plank, but everyone does it. No one has any problem. You tell them to put on the HMD, walk across the plank. 90% of the people fall off. People are shaking. They're petrified. Right? Why? You tell them, reach down. The plank's right there. You're on the floor. Walk across. People are petrified. This, more than any other type of data, to me, shows efficacy of this. It shows that immersion works because people believe, we want to believe what we see, we want to believe what we experience, and the bottom line is that we will. And that's, there's a few other reasons, but that's hugely important in driving this technology. Next. Besides what I just mentioned, another reason why VR works so well is that we have this willing suspense of disbelief. So immersion occurs when we stop thinking about what we're seeing or hearing or feeling and just experience the virtual worlds and the interactions as normal, right? So you can have cognitive inhibition. You can say, that's not quite right. But generally, this is an unconscious thing. There are some people that VR doesn't work at all for. They can't suspend their disbelief. They focus on differences. They look and they say, that virtual isn't quite the same as the physical. That crack isn't right. And there are all types of hacks and differences. And so when you focus on that, that's true. But what's amazing to me is that for the vast majority of people, it's the most compelling experience that they've had when they're not in the real world. In a lot of ways, this presence is amazing that it occurs. You can do it with poor graphics. So the graphics in our expensive HMD are quite good, but in the Oculus they're not very high. You have a limited field of view, so you might have 60 degrees field of view. We see over 180. Well, I don't, but most of you do. Most things are in VR is just showing vision, right? So we have incomplete models, so rarely are you seeing your hands and your feet. This would be completely unacceptable in the real world, but it absolutely works here because of this willing suspense of disbelief, because of immersion, because we're fooling the nervous system, and it really doesn't mind being fooled if you do it in the right way. And another big reason it works is because we have these real normal coupling between perception and movement. So when you give the neural signal to move your head, you expect a lawful flow of information across your retina, and that's what you get in these systems. Okay, next. So just briefly, augmented reality, we've gone through virtual reality. Augmented reality has gotten a lot of interest lately. There's a lot of implementation in the real world. There's lots of commercial applications. Everyone's talking about it. Essentially, augmented reality is simply, think of it as just superimposing electronic information on the physical world. So the difference here between augmented and virtual reality is that with virtual reality, the experience in the HMD is only virtual, right? You're totally disconnected. With augmented reality, you have both virtual information, but that virtual information is overlaid on the physical information. And there's lots of different types of technologies that are out there, lots of applications. This figure is showing you just one example. A lot of people have heard of the Google Glass. That's essentially a monocle that you used, and so the person here is just seeing different types of information superimposed on the environment as they walk around. Another incarnation is using a camera, so you can just use an iPhone or a smart device. You look through the camera and it superimposes information. Here I think it's menus on when someone's looking at the physical food establishment. So are these distinctions clear between virtual and augmented? Yeah. Okay, next. So let's move on to information visualization with these technologies. I think it's expected. I'm going to argue that VR and AR are great tools for information visualization. They provide all types of benefits that other existing tools don't. I'll go through some here and then I'll go through some examples, again, very briefly. So one of the reasons that they're so great is this immersion. So we've talked about the importance of something being immersive. But why is it important for visualization? Well, it allows users to become part of their data. So essentially, it's more intuitive, and it's just much more easy for someone to understand something when they're inside the data, when they're actually feeling like it's something that they're acting within, than looking at external representation. So if you're just looking at graphs and charts and what have you. There's a lot of relevance here to education, which maybe some here have some interest in. I'd love to talk more about it. The dynamic interaction that I talked about is hugely important. So this allows for immediate experience of cause and effect relations. You can manipulate variables in real time and see how they change. You can simulate different models of many big data applications and show how the outcome changes depending on what type of simulation you're using. Other advantages, they're cheaper than other technologies. So there's no need for an expensive physical mock-up or models, which is great for when you're trying to visualize things like new construction, environmental planning, these types of things where people often use these crazy expensive physical models And then if you want to change them, you're screwed because you're going to go back to the drawing board and they say, all right, well, give us another 50,000. Not a problem in VR. It also allows for repeated usage, which is great for training scenarios. So this is where resource utilization is a big deal, where safety is a big deal. And as I'll talk about in an example coming up, these things can be dealt with. So my bottom line with respect to visualization is that, I'm agnostic to the data and to the technology itself. And what I mean here is that my goal, I'm not really interested in pushing a specific data agenda, especially when we're talking about visualization or a specific type of technology. But what I really want to do is to understand the best technology to convey meaning for a given situation, and then allow people, the user, whoever's using it, to make their own informed decisions based on the immersive firsthand experience. So, in other words, let people develop their own belief vectors. Let people develop their own perceptual state space based on how the data is best interpreted in their nervous system using the right technology. And that's what I'm trying to do with this, rather than forcing people to do what they are bad at. And what they're bad at, and this is really what the crux of the issue is when we talk about visualization. We are terrible at imagining things. What do I mean? If someone asks you to imagine anything, imagine a building, imagine a graph, whatever, what you imagine often has little connection with reality. It has little connection with how it actually looks. So for instance, if I were to ask everyone in this room, hey, give me a verbal description of the campus map of Maine, how would you do it? I've done studies like this. I bring people in, I ask them,
Which map?
Any map.
There's parking lots.
It's rhetorical. You don't need to do it right now. But I can bring you into a study. I've done this and I'll ask 20 people and I'll get 20 very different descriptions. And they're all largely ambiguous. They use different words. You get this prepositional vague, like something is over there. Over there conveys no meaning. Next. Now, if I give you an example of a map, it probably makes a lot more sense. It may not be the best. I'm not going to go on record to say it's the best cartology, but it's this is much easier than what you would have described. This essentially is the pictures worth 1,000 words phenomenon. But what I want to get at here is pictures are not always, they're not always created equal. And a good visualization, a lot of times you'll read, well, good visualization is about having high resolution, really high definition images. Crap, that's not true. That may help. But when you look at an HD TV, and I don't care how good a HTV it is, and you're looking at some sporting event, you don't think you're there. You turn your head and you see your living room, right? You don't see the stadium because the TV is fixed. All the things that we've been talking about are important: immersion, interactivity, willing suspense of disbelief. None of that is there. So these factors are really important for beneficial visualization. It's really why I push the idea of AR and VR. Okay, so I'm going to discuss a few examples here, the things that we've been working on in the lab. And my hope is really, again, for you to consider this, not necessarily the specifics of these examples, but how they relate to other simulations and other types of things that you're doing or interested in, and how there could be extensions to these. So, next. So this is an architectural visualization. This is an image of a modern apartment that we did for a company, an Australian company. This is in Brisbane. And essentially the goal here was to visualize a space for people to see before they're moving in. All right, and this was a great example, and I'll complain in a minute because you lose so much of it by looking at a screen. I mean, it's comparing apples to oranges. But when you're in this with the HMD and moving around, the couch that you see there is so real. We've multiple times had to stop people from sitting on it, right? Sitting on a virtual couch is bad for the insurance. But again, it shows that it really is an amazing, people are compelled. You would not normally sit on something that's not there. But again, the beauty of this type of visualization is that it allows us to do things that you can't do with other types of models. So whatever parameter that you're interested in, click of a button, we can change it. We can move the windows around. We can change the floor texture. We can change the vista that you see outside the window. That stuff's all very easy. And I know that there's people, I'm not sure if they're here, but I know that there's people in SSI, in other related centers here that are interested in things like the perceptual aspects and resource consequences of designing sustainable communities. And I think there's lots of interesting types of simulations and visualizations in that domain that could relate to this type of simulation. Here's my note. The examples that I'm showing today really fail as good visualization. They don't fail in the lab, but they fail here. Because these are 2D flat images. They're not immersive, they're not interactive. And this is a problem with how do you show VR, which is inherently all of these things, using traditional medium. It forces you to imagine. In the end of the day, it doesn't really work. But work with me here to try to imagine things after I've just told you that you're not good at doing it. What these things would look like. So next. So this is a scientific visualization. This is a simulation. This one was done by R.J. Perry. He's a student in the lab in conjunction with the Climate Change Institute here on campus. And we're looking at the Earth's radiational balance. We're showing that. And this is a great example of how we can do big data visualization. So with big data, it's often really hard to convey. We have these huge multimodal, multi-dimensional data sets, data from all different types of streams. And people are trying to show them on flat graphs and charts and all these different ways. And it's very difficult. And so with VR, it's much easier as the user can become, as I mentioned earlier, they can become immersed in the data and they can experience how things change in real time based on whatever underlying models or predictions are being simulated. So in this case, the simulation shows we're looking at albedo. How albedo varies where the user is looking as a function of things like weather, time of day, their location, and what have you. And so, CCI had all these data, as I said, and they just didn't have a good way to. They were trying to figure out a good way to visualize them. And so this really worked out nicely because it allows people to get into this model. And I think I'm not sure if my notes are correct. The yellow arrows here are, again, sunlight. The purple arrows are absorbed radiation. The blue are reflected from the clouds. Again, this makes much more sense when you're actually looking at it, but it allows the person to move around and look at all these different things and how different climate change models change based on these variables. And again, there's a lot of people that I think in this group that are using big data and different types of visualization. So I'd be really interested in talking with people about what are other potential applications. Okay, next. So this is work with Sylvia Allain, a student that was also in the lab, showing simulation of essentially how different trees germinate and grow. And what's cool here is that when you're looking at this model in the HMD, we can play with the time scale, so we can speed it up. We can look at how different species compete with each other for resources in the ecosystem. We can play with a bunch of different variables. Again, I'm not a forest ecologist, but I can imagine lots of applications for this type of VR simulation for people that are interested in forests. So things like, what if we were simulating different models of forest growth trajectories after, different cutting or different harvesting techniques. There's different ways you can do this. So how would it look with different simulations? Could we simulate different forests, how fast they would grow back after natural disasters? So again, ideas to think about. Next. So this one is a demo that we did with Maine Emergency Management. And we're simulating emergency response training scenarios. So call this the Boardman demo. We simulated setting one of my colleagues' labs on fire. And this is looking at it, I think, 7 minutes into the burn. So in this demo, what we're experiencing here, so you get real smoke propagation. So as people move around, they can go down and get the correct change in how the smoke would look. They can hear the fire spatialize as they move and gets closer to them. They can hear the alarms. We can simulate augmented reality. So imagine that they're coming in here and they have a thing in their hand that they're holding. Well, if the smoke is occluding the building or some of it's collapsed, we can actually show by previous maps where offices where people might be based on an augmented reality view, so it can help guide the search. Essentially, the advantage of this type of training simulation is that it's much cheaper, it's much safer, and it allows this continuous use. So you know, if you're doing a real disaster training scenario, it's very expensive. It takes a lot of resources, and once you burn the building, it's done. So this is something that a lot of people are interested in saying, hey, can we teach people how to use these skills and do these skills in VR and have them do it, you know, have that guide them once they're in the real environment. Okay, next. All right, so this is a demo in the lab that's using augmented reality and computer vision for edge detection. And essentially, we're interested in hearing how to help prevent falling in older adults. So, aging is a big issue in Maine. We have the oldest state in the union. We have a lot of people that live in rural places. They want to remain in their homes, but falling is a really big issue. There's something like 30 billion a year that's spent in accidental falls, and lots of people die. And it's a real problem. So this image is showing a common falling problem scenario. A lot of times people fall because their vision's going down a little bit, their contrast sensitivity is going down as they age. And so something like seeing granite steps in a granite sidewalk or a curb or whatever can be a problem. So our solution is superimposing edges on the stairs. So instead of going out there with your spray paint can and trying to spray these things or do something that retrofits the environment, let us use augmented reality to superimpose high contrast lines that help you to detect features or help you to detect important elements in the environment, something we're calling compensatory augmentation. I think that there's a huge amount of examples of where this could really affect and improve the safety, the independence, and really the quality of life of a lot of people. We can think about lots of different things that you could augment in this method. This is something that's really not being done. Next. Okay, I'm running a little behind, but I am finally to the advertised final visualization, what we're talking about related to the SSI project. So the goal here was to use augmented reality and virtual reality techniques to improve visualization of new wind energy installations. Okay, so we know, and most of you know, all the problems that are here. Some of them, I mean, people are worried about how new turbines will look. They're worried if they'll disrupt their vista from, you know, have a beautiful porch looking out over the ocean. Last thing I want is a whole bunch of huge turbines in front of it, or from a nearby park. Or how will it sound? Is it going to kill birds? Is it going to negatively affect tourism and, you know, other aspects of the community? There's a lot of concerns. We're not addressing all of them, but there really are important concerns. They're big problems, and they're mostly problems of perception. So what I mean is that there's this dearth of techniques out there right now that that show people what the sight and sound characteristics of a wind installation actually will be. And what's more problematic is what is out there and what is being used is often just not very compelling. It's not very helpful. So the normal methods that people are using, that, you know, you take a GIS map, you might take a 2D diagram, a generic terrain image. If you're really lucky, you might get a single sound source, like something in the corner. Okay, do you understand now what it's going to be like? So this figure is just showing you. This is of the process. So we have a figure here of a GIS wind farm site map. So this is kind of this top-down view of the location of the property, the turbine, how it relates to the surrounding landowners. We see the turbine in a generic landscape. And so my question really is, you know, what would this visualization help you really know what this installation would be like? Right? Would it help you know what it's going to be from your house or from the park or what have you? I think the answer is clearly no. Right? So this gets back to the imagination problem that I keep mentioning. This is a real problem, and it's especially a problem when we have data that's unclear or inaccurate. So, feeling very clever, we have our solution, and it's, I think, working fairly well. So we decided that we really want to evaluate, look at this issue and evaluate how we can introduce virtual reality and augmented reality to model real wind, wind energy installations. And the goal here is to allow people to let the data speak for itself. Let people determine their own perceptions based on what it really would be like. So the project has progressed in kind of two tracks. They're both ongoing. I'll just briefly describe both of them and what we've done so far. So next. Okay, so we decided to use, for the first track here, well, in both of them, but we decided to use as our test bed Mohegan Island, as this is a area that's proposed for an offshore turbines, and correspondingly, it has there's been a lot of concerns about what these things will look like and how they'll affect the area. So track one of the project used what we have called the development of a static site visualization model. And really, all this means is that we're looking at visualization based on a predefined location on the island. In this case, we use Lobster Cove as it's closest to the turbines where they're proposed, and it's also an important popular tourist location. Okay, next. Okay, so this figure shows a simulation that you would be seeing through the iPad, and this is kind of you can think of as an AR simulation. So what you're seeing here. And again, you're seeing this as a 2D incarnation. But you're seeing the beach, you're seeing the ocean, and you're seeing the 3D turbines. What I want to clarify is that if you're standing at Lobster Cove, and this is where people were doing this, and you're looking out, you would just see the beach and the ocean. You wouldn't see anything. But when you look through the iPad, now you're able to see what's physically there, but you're also seeing how the turbines would look once they're actually built. We're also using gyros and accelerometers in the iPad, so you can turn in place. You can't move, but you can turn in place and you can see what's around you in that vista. So if behind you there's a house, and you can turn around and see that on the iPad as it's actually there in real time. So it's not immersive, but it allows you to see this 360 field of view. Does that make sense? Okay, so just a quick summary of the development process here. So first we sent a number of students to the island. I don't know if anyone's here, but a bunch of our group went at 6 o'clock in the morning, which was amazing, and went over with some lobster people and people looking at birds, and it was quite an event. Anyway, they took panoramic images from this location and wrapped the images around a cylinder. So you can kind of think of it as just kind of wallpapering these images. Essentially what we're trying to do is create spherical imagery that allows the user to look around, so to give that 360 view at the site that we're talking about. We then got the 3D models of the two turbines, and this was as of May 2013 at least. 2014, my lord. We got these from the DIC here on campus, and we got the GPS data from where these turbines are actually proposed to be. Okay? So then what we did is we combined the GPS data from the turbines with the GPS data from our spherical images, and we therefore created a simulation of the environment and the 3D turbines. We then took this wonderful simulation and dumped it on the iPad. And so that's how we, in a kind of a course, synopsis, how we developed this simulation. Okay, then armed with these AR renderings, a survey was conducted of tourists on the island. So we took, and this isn't my research, so I'm really not going to talk about it. This is the other people that were in the project. But we wanted to assess what are the effects of the perceptions of these turbines on people's potential to visit the island. So, as I understand it, the participants they're on the island, they were brought to Lobster Cove, they're allowed to see the AR renderings, and then they're given a whole bunch of different questions. Here's just, next slide, an example of just one of them, and again, this work is all still being analyzed by the other members of this group. But essentially, something like this: what's the effect of the construction of the offshore turbines on your likelihood of visiting the island based on what you just saw from our images? And 88% of the people, and this is I think out of about 180 people, stated that they would have no change in the number of visits based on what they saw here. So, at least for tourism, people that are worried about that, that's a good sign. All right, next. So, the second stage of this project involves creating a fully immersive virtual simulation of Mohegan Island and the turbines. This time we're doing it in the lab, and this is very much work that's still in progress. So the difference here is that rather than using the iPad, And rather than using a static location, we're now using the HMD with really in immersive VR. And so we're thereby providing this sense of a really rich sense of presence with really high resolution 3D imagery and unrestricted movement in the virtual world. So that's kind of a big difference. So what you're seeing here is the same figure. You're seeing the same location and viewpoint as you saw on the iPad, but now you get this high resolution renderings, you're getting full movement. And so here, if the person wearing the HMD wants to lie on the beach and look at the turbines, they can do that. If they want to jump up and down, they want to wave, they want to give it the finger, whatever. That's all possible because it's fully immersive. So when this is complete, users will be able to virtually walk around, as they normally would see and hear the turbines as they will, look and sound once created from anywhere on the island. And so that's really a big difference. So the process here essentially is that we're, as I said, we're recreating the entire Mohican Island terrain. So we're using a bunch of different data sources, everything from GIS and GPS to LiDAR, and a whole bunch of detailed information from a mapping company that we're working with. So the result is that, in this case, we'll be able to know exactly the location, the height, the orientation of the user when they're looking at the turbine. And this will obviously affect how it will be perceived. And so we can give a much more accurate view. So, I'm really excited about what's going on here. We're developing a completely new tool for wind energy visualization. It solves a lot of the problems that are out there for existing tools and does a lot of things that are currently not expensive or not possible. It's inexpensive, it's highly realistic, it's fully immersive, and we can finally allow people to use real data to make informed decisions and to figure out what their perceptions actually are. This simulation can also be used in the lab, so it's going to be, since it's in the VR, it will be in the lab, but we can use it in the lab to run experiments now, so to assess opinions, to assess feedback. It can be used for creating new site visualization models. It can be used for showing demos to high impact stakeholders, or really just anyone. You're a tourist, you're a local, you want to see what it's like. So frankly, I think there's all types of applications here. Again, people that have ideas, I'd love to talk to them. Next. A lot of research directions here to go, all types of work that still needs to be done. I'll just mention a few areas that come right off the top. So we need to study movement more. We need to be able to figure out how the best way for people to interact with the environment, the virtual environment, when they're in the lab. So the next stage is to use the new motion capture tracking system that we have to really nail allowing people to freely walk around and become fully immersed. We've done a little bit of that for the immersive demo so far, but there's a lot of complexities that we're still working out. Another big issue that has huge implications is how do we create immersive simulations that can integrate real-time data streams? So there's all these streams. For this particular project, we have things like different weather, illumination changes, wind speed, tidal conditions. These things are all dynamically changing. How can we integrate those into the real-time models? We also need a lot better and more accurate modeling of multimodal information. I'm particularly interested in auditory modeling here. How do we get rendering of ambient noise or realistic changes? So how would these things sound different if you open or close your windows? That's a big deal, because if the window's closed and you don't even hear it, that's something that people should know. What about the effects of trees and foliage? None of these things are being tested at all in sound evaluations. What about wind and ocean sounds? That adds a whole bunch of ambient noise. So we want to improve the realism of these types of parameters, and we need to do that if we're going to achieve true presence. The bottom line is that auditory information is hard to get, so this is something that we're working on. Next. So I'm running out of time. There's more I could talk about, but I will stop. But I'm excited about potential collaborations here. I'm excited about talking with people about this more. And anyone that wants to come over and kind of get, I promise it'll be just orders of magnitude better when you're actually doing it than looking at it on these screens. You're welcome to come to the lab. Let us know. So, thank you.
So Nick, this is Ruth. So when somebody is gloves and whatever else you've got come up to, are you actually tracking all their movements and taking data on that you can then use to, in terms of more of a long-term experiment?
Yeah, everything's being tracked. So imagine this room has, in our big room, we have 8 cameras that are around, and there's LEDs that are on the HMD. And there's also inertial trackers that are doing IMUs that are tracking the pitch, roll, and yaw. So as they're moving around and as you're doing whatever you want, spinning, moving, kicking, everything's being tracked, and that's what allows us to update the information. So if there's something, if there's a desk 10 feet in front of you, and we're not tracking you moving, then we can't show that you're getting closer to the desk. But we're tracking with very high precision, and the new trackers we have allow you to track different parts of your body. So you can track a hand now, not just the head, where before that was very hard. So you can track people, different joints, different movements, different actions, all in real time with quite high precision.
I actually have a follow-on question.
Yeah.
So does it work the other way too, Nick, though, where the data you're collecting could actually be used as feedback on the experiment?
Explain what you mean.
So, for example, I know you're having a lot of interest in psychology, but is what they're experiencing and their movements and their reaction to what's going on, are you tracking that?
Yeah. So in the behavioral experiments that I run, those log files are hugely important because we can cross-correlate. Oh, they just saw a big tiger, and that's why they jumped or kicked or whatever. So
Right.
we can look at those responses, or I do a lot of navigation research, so we can look at where they're walking, what they're seeing, how people are getting lost or not getting lost, and use those logs as a really rich data set.
Question up front.
On the full island map of Monhegan Island with
Yeah.
the immersion, have you integrated buildings? And I was wondering also, with that, have you figured out how to, if you're walking in a direction in the VR area, not have someone walk in a straight direction and hit a wall in the real world?
Yeah.
But think they're walking, 5 miles. In the
So yeah, so you hit a 2 questions. The first one's easy. Yes, we're including buildings and things. Second one's hard. So you hit the key point. How do you provide infinite movement in a finite space? So even if you can freely move, if the virtual world has 50 feet ahead of me and this room only has 25 feet, I'm going to face plant the wall in 25 feet. So how do you deal with that? Well, that's a perennial problem for free moving VR. You can do things if you have a really, really huge space. You can actually turn people in a circle that's sub-threshold so they don't realize they're turning, so you can get them to walk very long distances. They think it's straight and it's really a circle. And you can play with the gain and things. They have these hamster balls that you can get in and kind of walk in. But right now, we're essentially, the way that we deal with this, and we haven't done huge environments yet, but you essentially will walk in a space and then we'll transport you and move you to a different space. And so essentially it's like little jumps, essentially. So if you're in a park and we'll say, okay, now we're going to move you to your house, and we try to make it more discrete. So if you are walking a mile, you can actually do that in the lab. But that's one of the challenges of free movement that we really need to think about. And this is true for anyone that's doing large-scale navigation with immersive VR. How do you do that so it's compelling?
Have you looked into using other technologies such as 3D scanning to import real models of actual objects into your simulations?
Yeah, it's a good question. We're not. Some people are doing that, and the real 3D scanners are quite expensive. We talked a little with some people at CCI that were thinking about getting one. So the short answer is no. But from the visionary standpoint, I'm familiar with that work, and that isn't a neat way to get really highly rendered realistic models in there.
Pertaining to your first question about the psychological data sets, are there any distinct reactions in people in virtual reality that would differ from the reaction to a similar situation in the real world? Like, for example, that balance beam 16 feet above the ocean, would there be some biological markers that would be unique to one of those two situations?
Yeah, good question. So, this is one of the things that really says, well, is the efficacy of this technology, for it to be valid, we have to see some correspondence between what happens in the real world. there isn't a lot of physiological data. Like, so if we put people on the 16-foot real plank and the virtual plank, are they equally as scared? There is quite a bit of behavioral data on getting lost in buildings. So if you learn in a virtual building, you transfer to a real building, or you do the opposite. That data suggests that it's very, very similar, but there are some weird perceptual compressions. So if you close your eyes here, look at something 10 feet away or 15 feet away, and walk to it, stop when you think you get to it, we're very good, out to about 20 meters. In virtual reality, it's compressed. It can be compressed 50%. No one knows why. They've done tons of studies. But you can adjust for that. So if you know that there's going to be a 50% compression, then you can set it at 150%. So if you understand the perceptual offsets, you can play with that.
This kind of follows up on that question, but do you ever use biosensors or biometrics connected to the person doing VR that's like maybe measuring heart rate, respiration, alpha waves, things like that? Does that ever come into play, or is that valuable?
It's very valuable. We don't do it, and I want to do it. Do you do it?
I actually started playing around with a biosensor kit recently.
Yeah, I'm really interested in doing that. So exactly for the guy that worked on this demo, I said, let's just get at least a heart rate monitor on so we can look at the spikes. We're doing a lot of driving research, and I would love to be able to get more physiological data. And as long as we can get the data stream out of those sensors, that would be great to implement in the models. It's not done enough. It really should be done more.
You mentioned earlier about how in mapping physical buildings, you usually take the schematics and data information that they provide. How do you use that with the island that you mentioned, where I'm sure there aren't schematics of the brush and everything?
Yeah, it's a good question. So we're working with a data mapping company that's been doing a lot of work on that island for a different reason. They have a whole bunch of LiDAR data and other really, really precise mapping data that they've collected that we're using. In general, that can be difficult because you can get 3D models and that's great, but that doesn't include, in a building, it doesn't include things like this lectern generally. Outside, it might not include a bush. So that is often a problem. In this case, and we're still working on that, but in this case, we think we have the solution because we're working with a company that's also interested in doing this for a different reason.
For the setup on the island, how do you take into consideration how sound waves bounce off different surfaces or shape of the landscape? Does that come into account?
You want to come and do this too? Sound propagation is hugely important. VR, I like including auditory information. Sound is harder than vision in a lot of ways because the modeling of the propagation models are not as well specified. I mean, you know that sound drops off by the inverse square, but the short answer is we are trying to do that and thinking about doing that, and that's a big part of the future. Right now that is not being done at all, but it absolutely makes a difference. So the sound coming off those turbines, as I said, when it's going to go through a foliage hedgerow in front of your house, is totally going to change the parameters of how it deflects and how it reflects and how it comes to you. So that's stuff that you can do with auditory modeling, and we're interested in, that's where we're kind of moving towards, but that's kind of the cutting edge. It really isn't being done in any of these types of visualization models.
Recently, in my studies, in the past half year or so, just from this because you brought up the Oculus Rift in the slide, but the Oculus Rift or whatever the name of the company is, they were bought out by Facebook.
Yeah.
And I was just curious, as someone who makes their work doing research in virtual reality, what you made of that decision. Because, for someone like me who doesn't have a lot of experience with that, it can kind of make sense of it. At the same time, it's also kind of just like, why would they need virtual reality?
Well, there's the obvious, the initial knee-jerk, this cool small company selling out to Facebook, and some people in the lab were upset, I'm like, well, you've been doing demo, beta work with this that now is highly desirable to Facebook, so that's pretty good to have on your resume. From the standpoint of why Facebook wants it, they're very interested in the social interaction. So how do you, instead of just talking about, chatting or doing something, doing something very 2D, non-immersive when you're communicating. What if we now can put you with your social network where everyone's wearing Oculus, everyone's able to move around, and you actually think that you're in the same room together. You know, you're at a game together, you're doing tasks together. I think they see huge potential for the social interactions and the social psychology component of it that really haven't been pushed that much previously in a commercial level. There's a lot of social psychology work with virtual reality that shows very similar. Biases are the same. People that have stereotypes, they're almost exactly the same in VR as out of VR. And so they know they can tap a lot of this underlying kind of social connectivity, but now trying to do it in VR and doing it remotely is kind of where they want to go.